The attractive intermolecular forces are often called van der Waals forces in the honor of Dutch physicist Johannes van der Waals. Van der Waals forces can be classified into dispersion or London forces, dipole-dipole forces, and dipole-induced dipole forces. Let's study each of them in detail, starting with the dispersion forces. The existence of dispersion forces was first suggested by Fritz London, and hence these forces are also known as London forces. We know that atoms and non-polar molecules have no dipole moment because their electron cloud is symmetrically distributed. However, due to the constant motion of the electrons, an atom or molecule can develop an instantaneous or transient dipole when its electron cloud is distributed asymmetrically about its nucleus. Let's understand this through an example. Suppose we have two atoms labeled as A and B in close vicinity. For a moment, let's assume that the electron cloud distribution in atom A becomes unsymmetrical. That is, the electron cloud is more on one side than the other. Due to the unsymmetrical distribution of the electron cloud, an instantaneous dipole is developed on the atom A. This instantaneous or transient dipole distorts the electron cloud on the other atom. That is, atom B, which is close to it. As a result of this, a dipole is induced in the atom B. The temporary dipoles of atom A and B attract each other. This force of attraction between the two temporary dipoles is known as dispersion force or London force. This force is important only at a short distance, which is limited to 500 picometers and is inversely proportional to the sixth power of the distance between the two molecules. Another type of intermolecular force is dipole-dipole forces. The dipole-dipole forces are attractive forces that act between the polar molecules with permanent dipole. The ends of the dipoles in a polar molecule possesses partial charges which are represented by the Greek letter delta. For example, in hydrogen chloride, due to the greater electronegativity of chlorine, it attracts the electron cloud more towards itself, and thus its end has a partial negative charge and the hydrogen end has a partial positive charge. The attraction between the positive end of one polar molecule and the negative end of the other polar molecule forms the dipole-dipole forces. The more polar the molecule, the greater is the strength of its dipole-dipole interaction. Due to this, the boiling point of polar covalent compounds is relatively higher than that of non-polar covalent compounds. Dipole-dipole forces are stronger compared to the other London forces. But due to the involvement of only partial charges, they are weaker than the ion-ion interactions. The dipole-dipole interaction energy between the polar molecules is inversely proportional to the sixth power of the distance between the two polar molecules. Polar molecules can interact both by dipole-dipole forces and also by London forces of attraction. The third type of forces are dipole-induced dipole forces. These attractive forces operate when a polar molecule with permanent dipole induces a dipole in a non-polar atom or molecule by deforming its electron cloud. Consider the nonpolar chlorine molecule brought in the vicinity of a polar molecule, such as water. The permanent dipole of water molecule polarizes the electron cloud of chlorine and induces dipole on the electrically neutral chlorine molecule. Thus, dipole-induced dipole interactions come into existence between water and chlorine molecules. The induced dipole moment depends upon the dipole moment present in the permanent dipole and the polarizability of the nonpolar molecule. Larger the size of the nonpolar molecule, higher is the polarizability, and hence greater is the strength of the attractive interactions. In this case also, interaction energy is inversely proportional to the sixth part of the distance between the two interacting particles. A special case of dipole-dipole interaction called hydrogen bond exists in the molecules with highly polar NH, OH or HF bonds. This intermolecular force is stronger than the van der Waals forces of attraction, having interaction energy of the order of 10 to 100 kilojoules per mole. Therefore, hydrogen bond is a powerful force in determining the structure and properties of many compounds such as proteins and nucleic acids. Have you ever wondered why it is very difficult to compress the solids and liquids? Intermolecular forces can also be repulsive in nature. When two molecules are brought closer, the repulsions between the electron clouds and between the two nuclei of the molecules come into play. The magnitude of repulsion increases rapidly with the decrease in the distance between the molecules. In solids and liquids, the molecules are already close to each other, and hence, when we try to compress them, the repulsive interactions would further increase. Hence, they resist compression. The physical state of a substance not only depends on the strength of intermolecular forces that exist between its atoms or molecules, but also on the thermal energy of atoms or molecules. The energy of a body arising from the translational, rotational, or vibrational motion of its atoms or molecules is called the thermal energy. It is the measure of the average kinetic energy of the constituents of the matter and is directly proportional to temperature of the substance. The intermolecular forces of attraction between the molecules try to bring the molecules closer. On the other hand, the thermal energy possessed by the molecules, which results in the movement of molecules, tries to keep them apart. The balance between the intermolecular forces and the thermal energy of the molecules is responsible for the physical state of matter. In gases, the intermolecular forces of attraction are the weakest, while thermal energy is the highest. While the compression brings the molecules to close vicinity, the lowering of the temperature brings about the liquefaction of the gases by decreasing the thermal energy of the molecules. Of the 117 elements known so far, only 11 are in the gaseous state at room temperature and pressure. The gaseous state is the simplest form of matter. This is why all gases show almost identical physical behavior regardless of their chemical nature. They are characterized by the following properties. Gases have no definite shape and volume, and hence assume the volume and shape of the container.
Gases are highly compressible, which means that when the pressure increases, the volume of the gas decreases. Gases exert equal pressure in all directions. Gases intermix equally and completely in all proportions without any mechanical aid. Gases have lower density than solids and liquids. The behavior of gases is governed by gas laws, which define the relationship between measurable properties such as volume, V, pressure P, temperature T, and the number of moles N. These properties are interdependent and describe the state of the gas. The four main gas laws are Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Boyle's law expresses the relationship between volume and pressure. Charles' law expresses the relationship between volume and temperature. Gay-Lussac's law expresses the relationship between pressure and temperature. And Avogadro's law expresses the relationship between volume and number of molecules of a gas. Let us discuss each of these laws in detail. In 1662, Anglo-Irish scientist Robert Boyle, after conducting various experiments, concluded that at constant temperature, the pressure of fixed amount of gas is inversely proportional with its volume. This is known as Boyle's law. Mathematically, Boyle's law can be written as P inversely proportional to V at constant temperature T and number of moles of the gas N. Or P is equal to K by V, where K is a proportionality constant, whose value depends on the temperature and number of moles of the gas. On rearranging the equation, we get PV is equal to K. Or, in other words, at constant temperature, product of pressure and volume of fixed amount of gas is constant. For example, if N moles of a gas A occupying volume V1 at pressure P1 expands to volume V2 and pressure P2 at constant temperature, then P1V1 is equal to P2V2, which is constant. Now consider N moles of gas B at pressure P1 and volume V1. Let us now slowly increase the pressure, keeping the temperature constant at T1. We observe that volume of gas decreases as the pressure increases. If we plot this variation of pressure versus volume on XY graph, we get the given curve. Let us now change the temperature of the gas to T2 and repeat the same process by keeping the temperature constant at T2. In this case, if we plot the variation of pressure versus volume, we get a different curve. From this, we can conclude that each pressure versus volume curve corresponds to a different constant temperature for a given amount of gas. These curves are known as isotherms. Similarly, we can plot variation of pressure against 1 by volume. We get straight line for each constant temperature. These straight lines pass through the origin. The next law is Charles' law that describes the relationship between volume of a gas and its temperature. Jacques Charles and Gay-Lussac studied the relationship between volume and temperature of gases independently. They concluded that for a fixed mass of gas at constant pressure, the volume of gas increases with increase in temperature and decreases on cooling. They found that when pressure remains constant, a fixed mass of any gas expands or contracts respectively by 1/273 of its volume at 0 degrees Celsius for every rise or fall in temperature by 1 degree Celsius. Let's understand this through mathematical expression. Let V0 be the volume of a fixed mass of a gas at 0 degrees Celsius, and let V be its volume at temperature T degrees Celsius at same pressure. Then, volume V at temperature T is equal to V0 plus V0 divided by 273 into T. Or, V is equal to V0 into 1 plus T divided by 273. Or, V is equal to V0 into 273 plus T whole divided by 273. Let this be equation 1. We know that T plus 273 is nothing but absolute temperature in Kelvin scale. Writing T plus 273 as T, we get V is equal to V0 into T divided by 273. But for a given mass of a gas, V0 by 273 is equal to constant. Therefore, V is equal to kT, where K is a constant. Remember, temperature T is in Kelvin scale. This is a mathematical expression for Charles' law, which states that the volume of a fixed mass of a gas is directly proportional to its absolute temperature if the pressure is kept constant. If a given gas occupies volume V1 at T1 temperature and volume V2 at T2 temperature, then by Charles' law, V1 by T1 is equal to K constant, which is in turn equal to V2 by T2. Therefore, the equation can be written as V1 divided by T1 is equal to V2 divided by T2 is equal to K. This is called the Charles' law equation. For a given amount of gas, if we plot the variation of volume versus temperature at different pressures, we get different straight lines corresponding to each pressure. These lines are called isobars. You can observe all the straight lines on extending to zero volume. Intercept the temperature axis at minus 273.15 degrees Celsius. From the graph, if we substitute the value of temperature as minus 273 degrees Celsius in equation 1, then volume at minus 273 degrees Celsius becomes 0. Thus, we can conclude that the volume of a gas would be reduced to 0 at minus 273 degrees Celsius. The temperature minus 273 degrees Celsius is called absolute zero. This is the lowest temperature that can ever be reached. At this temperature, the molecular motion of gases will stop and will cease to exist. The next law is Gay-Lussac's law. According to Gay-Lussac's law, at constant volume, pressure of a fixed amount of gas varies directly with the temperature. In other words, at constant volume, temperature of a gas increases with increase in pressure and decreases with decrease in pressure. Mathematically, Gay-Lussac's law can be written as P is directly proportional to T, or P is equal to kT, where K is the proportionality constant. The numerical value of the constant K depends upon the amount of the gas taken and the volume. This law can also be derived by combining Boyle's law and Charles' law. If we plot pressure versus temperature for a given volume of a gas, we get straight lines corresponding to each volume. These lines are called isochores. The fourth gas law is Avogadro's law. In 1811, Italian chemist Amedeo Avogadro stated that at same temperature and pressure, equal volumes of gases contain same number of molecules, irrespective of their chemical and physical properties. For example, consider 1 liter of hydrogen gas and 1 liter of oxygen gas. Then, according to Avogadro's law, at same temperature and pressure, both 1 liter of hydrogen and oxygen contain equal number of molecules. Mathematically, Avogadro's law can be written as V is directly proportional to N, where V is the volume of the gas and N is the amount of gas or number of moles of the gas. Replacing the proportionality sign by proportionality constant K, we get V is equal to Nk.
We know that volume, the number of moles, pressure, and temperature are the 4 interrelated properties that describe the behavior of gases. The relationship between these properties is described by 3 laws. They are Boyle's law, Charles' law, and Avogadro's law. Boyle's law describes the relationship between pressure and volume. It states that volume is inversely proportional to pressure at constant temperature and number of moles. Charles' law describes the relationship between temperature and volume. It states that volume is directly proportional to temperature at constant pressure and number of moles. Avogadro's law describes the relationship between volume and number of moles. It states that at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles present in the gas. On combining these 3 laws, we get the ideal gas equation. However, when we introduce a constant of proportionality, R, then the equation can be written as V is equal to R into N into T divided by P. Here, R is known as the universal gas constant. To find the value of R, we need to rearrange the equation and substitute appropriate values of P, V, N and T. For example, under standard conditions of temperature, that is 0 degrees Celsius or 273.15 Kelvin, and pressure, that is 1 atmosphere or 101.3 kilopascal or 10 to the power of 5 Pascal, 1 mole of a gas occupies 22.4 liters or 22.4 cubic decimeter. On substituting the values in the equation, we can get the value of R as 8.314 joules per Kelvin per mole. We have learnt that ideal gas equation is a relation between 4 variables: volume, pressure, temperature, and number of moles of a gas. If we vary temperature, volume and pressure of fixed amount of gas, that is, keeping the number of moles N of the gas constant from T1, V1 and P1 to T2, P2 and V2, then using ideal gas equation, we can write P1V1 by T1 is equal to NR and P2V2 by T2 is equal to NR. Combining the two equations, we get P1V1 by T1 is equal to P2V2 by T2. This equation is known as combined gas law and is useful in performing calculating of any of the variable if other 5 variables are known. So far, we have identified the relationship between volume and the other interrelated properties using the ideal gas equation. Next, let's move on to learn about an equation that relates density and molar mass for gas. To understand the density and molar mass of a gaseous substance, we have to rearrange the ideal gas equation to N divided by V is equal to P divided by R into T. On replacing number of moles N with mass of the gas M by M, we get the equation M divided by M into V is equal to P divided by R into T, where M is molecular mass of the gas. We know that M by V is equal to D, where D is the density of the gas. Thus, we can rewrite the equation as D divided by M is equal to P divided by R into T. On rearranging the equation, we get the relationship to calculate the molar mass of gas as M is equal to D into R into T divided by P. The various gas laws that we have learnt establish the relationship among pressure, temperature, and volume occupied by a certain number of moles of a gas. But air is a mixture of various gases. So how do we know the pressure of a particular gas in the mixture? In 1807, John Dalton studied the pressure exerted by a mixture of non-reacting gases enclosed in a vessel. Based on these studies, he formulated the law of partial pressures. According to Dalton's law of partial pressures, the total pressure exerted by a mixture of 2 or more non-reacting gases enclosed in a vessel at a given temperature is equal to the sum of the partial pressures exerted by individual gases, that is, the pressure which these gases would exert if they were enclosed separately in that vessel at the same temperature. To understand this law, Let us consider 3 vessels of the same volume at the same temperature. Let the first vessel be enclosed with A moles of hydrogen exerting a pressure of 0.30 bar, and the second vessel be enclosed with B moles of oxygen at the same temperature exerting a pressure of 0.45 bar. Now, if we put both hydrogen and oxygen gases in the third vessel, the total pressure exerted by hydrogen and oxygen in the third vessel would be partial pressure of hydrogen plus partial pressure of oxygen. That is, the total pressure P total is equal to 0.30 bar plus 0.45 bar, which is equal to 0.75 bar. Generally, Dalton's law of partial pressures can be written mathematically as P total is equal to P1 plus P2 plus P3 plus and so on at constant temperature and volume, where P total is the total pressure exerted by the mixture of gases and P1, P2, P3, etc. are partial pressures of individual gases 1, 2, and 3 respectively. Let us now calculate the partial pressure exerted by each gas from the ideal gas equation. Consider a mixture of 3 gases 1, 2, and 3 enclosed in a container of volume V at temperature T, exerting partial pressures P1, P2, and P3 respectively. Now, by applying the ideal gas equation, the partial pressure of gas 1, that is P1, is equal to N1 RT divided by V. Partial pressure of gas 2, that is P2, is equal to N2 RT divided by V. And partial pressure of gas 3, that is P3, is equal to N3 RT divided by V, where N1, N2, and N3 are the number of moles of the 3 gases. According to Dalton's law of partial pressures, total pressure exerted by the mixture of gases P total is equal to P1 plus P2 plus P3. On substituting the values of P1, P2, and P3, we get P total equals to N1 RT divided by V plus N2 RT divided by V plus N3 RT divided by V. On simplifying, we get P total is equal to N1 plus N2 plus N3 multiplied by RT divided by V. On dividing P1 by P total, we get P1 by P total equal to N1 divided by N1 plus N2 plus N3. Here, RT and V get cancelled. Therefore, P1 by P total is equal to N1 divided by N, where N is equal to N1 plus N2 plus N3, or total number of moles. We know that N1 by N is equal to X1, where X1 is mole fraction of gas 1. For a mixture of gases, the mole fraction can be defined as the ratio of number of moles of an individual gas to the total number of moles of all the gases present in a mixture. On substituting the values, we get P1 divided by P total is equal to X1. This equation can be written as P1 is equal to X1 multiplied by P total. Similarly, for other two gases, we can express partial pressures as P2 equals X2 multiplied by P total and P3 equals X3 multiplied by P total. Thus, a general equation can be expressed as Pi equals Xi multiplied by P total, where Pi and Xi are the partial pressure and mole fraction of ith gas respectively. Thus, if the total pressure of a mixture of gases is known and the mole fraction of the gas is known, then the equation Pi equals Xi multiplied by P total is used to calculate the pressure exerted by an individual gas. Dalton's law of partial pressures is useful in calculating the pressure of the dry gas collected over water by the downward displacement in the laboratory. As we know that a gas collected over water is saturated with water vapor, it is said to be a moist gas. The total pressure exerted by a moist gas is equal to the sum of the partial pressures of the dry gas and water vapor respectively. The pressure exerted by water vapor, which is in equilibrium with water at constant temperature, is called aqueous tension. If the pressure of dry gas and the moist gas are represented as P and P, and the partial pressure due to water vapor commonly called aqueous tension can be expressed as P dash, then by Dalton's law of partial pressures, the total pressure exerted by a moist gas, that is, P is equal to the partial pressure of the dry gas, P, plus partial pressure of the water vapor, P dash. By rewriting the equation, we get the partial pressure of dry gas P is equal to total pressure of moist gas P minus aqueous tension P dash. We have learnt that the ideal gas equation describes the behavior of gases based on experimental observations. To understand the behavior of gases at the molecular level, scientists developed a theoretical model called kinetic molecular theory, KMT, or microscopic model of gases. Kinetic molecular theory is a set of 5 assumptions that describes the behavior of molecules in a gas. Let's discuss the assumptions and how they are justified in detail. Gases consist of very large number of extremely small particles called molecules, which are in constant, continuous, random, and straight line motion. During their motion, they collide with each other and against the walls of the container. The pressure exerted by the gas is due to the bombardment of its molecules on the walls of the container. The molecules of a gas are separated from each other by great distances. Hence, the actual volume of all the molecules of the gas is negligible when compared to the total volume occupied by the gas. This assumption is true as gases are highly compressible. Hence, the actual volume of all the molecules of gas is negligible. Attractive and repulsive forces between the molecules of a gas are negligible as they are much away from each other. We can state that assumption 3 is true as gases expand and occupy the entire space available to them, showing the existence of weak intermolecular forces of attraction. Hence, attractive or repulsive forces between the molecules of a gas are negligible. Individual molecules do not gain or lose energy as a result of collision. Therefore, collision between molecules is perfectly elastic. This assumption can be justified because during collision, the molecules do not settle down or slow down. The average kinetic energy of the molecules is proportional to absolute temperature. Assumption 5 is the result of the fact that when the temperature of a gas is raised, the molecules start moving faster. Thus, their individual kinetic energies increase and hence the average kinetic energy increases. Based on these assumptions, an equation for pressure of a gas is derived as PV is equal to 1 by 3 mnu square. This is called the kinetic gas equation, where N is the total number of molecules in volume V, m is the mass of the gas molecule, and u is the root mean square velocity of the molecules. Let us now understand the gas laws in terms of the kinetic molecular theory of gases. First, let's start with Boyle's law. Consider a given amount of a gas in a cylinder fitted with a frictionless piston. According to kinetic molecular theory, pressure exerted by a gas is due to molecular collisions on the walls of the container. As the number of collisions increases, the pressure of the gas also increases. The average velocity of molecules is constant at a given temperature. When the volume of a gas is decreased, the space available for the movement of molecules decreases. Then, the number of collisions on the walls of the container increases, resulting in an increase in the pressure of the gas. This means, as the volume of a gas is decreased, pressure is increased for a given mass of a gas at a given temperature. This is Boyle's law. Next, let's take a look at Charles' law. Consider a given amount of a gas at normal atmospheric pressure enclosed in a cylinder fitted with a frictionless piston. When it is heated, according to kinetic molecular theory, the average kinetic energy of the molecules increases. Then, molecular velocities increase, thereby increasing the number of collisions with the walls of the container as well as the momentum of each molecule. As a result, the piston is pushed outwards. The volume of the gas then increases. Hence, at constant pressure, when the temperature of a given mass of a gas is increased, its volume increases. This is Charles' law. Next, let's move on to Avogadro's law. Consider equal volume of two gases under the same conditions of temperature and pressure. Since the temperature of the two gases is the same, according to kinetic molecular theory, the average kinetic energy of the gas molecules should also be the same. We know that the pressure of a gas depends on the number of molecules present per unit volume, as well as their average kinetic energy. As the two gases have the same pressure and same kinetic energy, they must have an equal number of molecules per unit volume. This means equal volumes of all gases under similar conditions of temperature and pressure contain an equal number of molecules. This is Avogadro's law. Gases that obey the ideal gas equation are called ideal gases. The ideal gas equation is PV equals to nRT. If we plot a graph of PV versus pressure at constant temperature, then, according to Boyle's law, we should get a straight line parallel to the x-axis, as PV is constant at constant temperature for a fixed amount of gas. However, for a real gas, we find that the plotted line is not a straight line parallel to the x-axis. This shows that real gases, which include almost all the gases such as nitrogen, oxygen, hydrogen, and carbon dioxide, show a significant or an appreciable deviation from the ideal gas behavior. When we draw a plot between PV and P for these gases, we get two types of curves. The curves for hydrogen and helium, as shown, lie above the ideal gas curve, and these two gases show a continuous increase in PV with the increase in pressure. Whereas, for other gases such as carbon monoxide and methane, the PV value first decreases with the increase in pressure and reaches to a minimum. Then, this value increases with the increase in pressure so that it crosses the straight line of the ideal gas. Thus, a negative deviation is observed initially in the curve, followed by a positive deviation as shown in the graph. Let us observe the nature of the graph obtained for a real gas in a pressure versus volume plot. It is clear from the graph that at very high pressure, the volume occupied by a real gas is more than the volume occupied by an ideal gas. And at very low pressure, the volume occupied by both a real and an ideal gas are almost the same. Hence, at high pressure, these gases significantly deviate from the ideal gas behavior. Dutch physicist Johannes van der Waals gave an explanation for these deviations and modified the ideal gas equation in order to make it applicable to real gases. He observed that at low temperature and high pressure, the following two assumptions of the kinetic molecular theory do not hold good for the real gases. Assumption 1. There are no forces of attraction between gas molecules. Assumption 2. The actual volumes of the gas molecules are negligible when compared to the total volume of the gas. Let us see how the first assumption is modified and made applicable for a real gas by van der Waals. If the first assumption is correct, then the liquefaction of the gases wouldn't be possible. But we know that gases can be liquefied by decreasing the temperature and increasing the pressure. At high pressure, molecules of gases are very close to each other, and the intermolecular attractive forces start operating. These molecules then do not exert full impact on the walls of the container as they are dragged back by the attractive force of other gas molecules. Hence, the molecules strike the walls of the container with reduced velocity. Thus, we can say that the pressure exerted by the real gas is lower than the pressure exerted by the ideal gas. Hence, the pressure in ideal gas equation is corrected as P ideal is equal to P real plus A multiplied by N square divided by V square, where N is number of moles of the gas, V is the volume occupied by the gas, and A is the proportionality constant characteristic of a gas. In the second assumption, the actual volume of the gas molecules is negligible when compared to the total volume of the gas, which is valid only at very low pressure. But at high pressure, the molecules are restricted to move around in less volume, and hence the volume occupied by the molecules themselves becomes significant. Hence, the volume V in ideal gas equation is corrected as ideal volume minus the volume occupied by gas molecules, that is, V minus B, and for N moles of the gas, it is V minus NB. B is excluded volume, which is constant and characteristic for each gas. After substituting the two corrections of pressure and volume in the ideal gas equation, PV is equal to nRT, we get P plus AN square by V square multiplied by V minus NB is equal to nRT. This equation is known as van der Waals equation. Here, N indicates the number of moles and the constants A and B are called van der Waals constants. The values of A and B depends upon the nature and characteristics of a gas. The value of A is independent of temperature and pressure. The extent to which a real gas deviates from an ideal gas can be measured in terms of the compressibility factor Z. It is defined as the ratio of product PV and nRT. For an ideal gas, the compressibility factor Z is 1 at all temperatures and pressures because PV is equal to nRT. On plotting a graph of compressibility factor against pressure, we get a straight line parallel to x-axis at very low pressure. We find that at very low pressure, all gases have compressibility factor approximately equal to 1 and behave like an ideal gas. At high pressure, all the gases have compressibility value greater than 1. This means that these are very difficult to compress. At intermediate pressure, most of the gases have compressibility value less than 1. This means that these are easily compressible. Thus, we can conclude that real gases show ideal behavior when the volume occupied by them is so large that the volume of the molecules can be neglected in comparison to it. Hence, we conclude that the behavior of a gas becomes more ideal when the pressure is very low. The magnitude of this low pressure varies for each gas as it depends on the nature of the gas and the temperature. The graph shown here depicts the effect of temperature on the deviations shown by a nitrogen gas. The temperature at which a real gas obeys ideal gas laws over an appreciable range of pressure is known as boil temperature or boil point. The boil point depends upon the nature of the gas. The boil temperature of nitrogen is 332 Kelvin. Above boil temperature, real gases are difficult to compress and the Z value is greater than 1. Below boil temperature, real gases first show decrease in the value of Z, then reaches minimum, and with the increase of pressure, Z value increases continuously. Thus, at low pressure and high temperature, gases show ideal behavior. Let us see another significance of the compressibility factor. We know that compressibility factor for a gas is calculated as Z is equal to PV real divided by nRT. If the gas is ideal gas, then V is equal to nRT divided by P. On substituting the value of nRT divided by P in the equation for compressibility factor, we get Z is equal to V real divided by V ideal. From this, we can conclude that Z gives the ratio of the actual molar volume of a gas to the molar volume of it, if it were an ideal gas at that temperature and pressure. A gas can be converted into a liquid through a process called liquefaction. Liquefaction of a gas can occur only when the intermolecular force of attraction between the gas molecules are increased. So, how do we increase the force of attraction? It can be increased in two ways. The first method involves an increase in pressure of the gas at room temperature. When we increase the pressure, the gas molecules come closer to each other. This results in an increase in the intermolecular forces of attraction between the molecules, which leads to the liquefaction of gases. The second method involves a decrease in the temperature of the gas. As the gas gets cooled, the kinetic energy of the gas molecules decreases. This results in the decrease of the speed of their random motion and in the increase of the force of attraction between them. This ultimately results in the liquefaction of the gas. Sometimes, we need to use a combination of the both methods to liquefy a gas. For example, carbon dioxide, ammonia, sulfur dioxide, and hydrogen chloride can be liquefied either by increasing the pressure or by decreasing the temperature. There are some gases, however, which cannot be liquefied at room temperature even at very high pressure. These gases are called as permanent gases. Hydrogen, helium, and oxygen are examples of permanent gases. Irish scientist Thomas Andrews studied the pressure and temperature conditions of liquefaction of several gases. He established that for every gas there is a particular temperature beyond which, no matter how much high pressure is applied, a gas cannot be liquefied. This temperature is known as critical temperature. Critical temperature, Tc, can be defined as the characteristic temperature of a gas above which any increase in pressure will not result in the liquefaction of the gas. The minimum pressure required to liquefy 1 mole of a gas at critical temperature is called critical pressure, PC. The volume occupied by 1 mole of a gas at its critical pressure and at critical temperature is the critical volume, VC, of the gas. TC, PC, and VC are collectively called the critical constants of the gas. A point where there is no distinction between the liquid and the vapor state of a gas is called the critical point, and the gas at this point is said to be in the critical state. In 1861, Andrews studied these critical phenomena of carbon dioxide. In his experiments, he studied the effect of pressure on volume at different temperatures for carbon dioxide. He plotted this variation in volume and pressure at constant temperature, called isotherms, as shown in the graph. Observe the isotherm at 21.5 degrees Celsius. At low pressure, carbon dioxide exists as a gas at point A. On increasing the pressure, the volume of the gas decreases along curve AB. The liquefaction of the gas starts at point B and continues along BC, which is evident by the sudden decrease in the volume. Both liquid and gaseous carbon dioxide coexist in equilibrium along the line BC. At point C, the liquefaction is complete, and the increase in the pressure has little effect on the volume. This is because liquids are very less compressible. So, a steep curve CD represents only liquid carbon dioxide. When the temperature is raised further, the horizontal portion in the graph becomes smaller and smaller, and at 30.98 degrees Celsius, it is reduced to a point represented by E. This shows that above 30.98 degrees Celsius, carbon dioxide cannot be liquefied at all, no matter how great the applied pressure is. So the critical temperature of carbon dioxide was found to be 30.98 degrees Celsius, while the critical pressure PC is 73.9 atmospheric pressure and the critical volume is 95.6 milliliters. As you can see, all the ends of the horizontal portions of the isotherms are joined to form a dome-shaped curve as shown here. Point A represents the gaseous state, whereas point D represents the liquid state. All points within the dome-shaped area represent the existence of liquid and gaseous carbon dioxide in equilibrium. All gases on isothermal compression exhibits the same behavior as shown by carbon dioxide. Note that it is possible to change a gas into a liquid or a liquid into a gas, such that there is always a single state present by altering the conditions of temperature and pressure. For example, in the graph, as we can move from point A to point F vertically By increasing the temperature, point G can be reached by compressing the gas at constant temperature along the 31.1 degrees Celsius isotherm. As the curve FG lies above the critical temperature, increase in the pressure doesn't result in the liquefaction of the gas. Hence, curve FG represents the gaseous state. Now, if we move vertically down from point G by lowering the temperature, on crossing the critical isotherm at point H, we get the liquid state. Thus, at no stage during the process we crossed the two-phase region. This is called the continuity of state. To recognize this continuity, the term fluid is used for either a liquid or a gas. Thus, a liquid can be viewed as a very dense gas. A gas can be liquefied below critical temperature by applying pressure, and then it is called the vapor of the substance. For example, carbon dioxide gas below its critical temperature at 30.98 degrees Celsius is called carbon dioxide vapor. Let us start with vapor pressure. When a liquid is partially filled in a closed evacuated container, the molecules of the liquid that possess above average kinetic energies overcome the intermolecular forces that hold them in the liquid and rise to the surface. These molecules start escaping from the surface of the liquid and reach into the vapor state. The process by which molecules of a liquid go into the vapor state from the surface of the liquid at any temperature below the boiling point of the liquid is called evaporation. As the molecules escape into the vapor state, they get confined to a limited space above the liquid and start moving randomly. During their motion, they collide with each other, with the walls of the container and with the surface of the liquid itself. When these molecules collide with the surface of the liquid, they are attracted back to the liquid. This process is called condensation. During the initial stages of evaporation, the rate of evaporation is higher as compared to the rate of condensation. After some time, as the rate of condensation increases, the number of molecules present in the vapor state starts decreasing. Gradually, a stage is reached when the rate of evaporation becomes equal to the rate of condensation. At this stage, there is no change in the level of the liquid in the vessel, and the system is said to be in dynamic equilibrium, where rate of condensation is equal to rate of evaporation. At this stage, the vapor pressure of the liquid is referred as equilibrium vapor pressure or saturated vapor pressure. Thus, vapor pressure may be defined as the pressure exerted by the vapor present above the liquid in equilibrium with its liquid at a given temperature. Since the formation of vapor depends on the temperature of the liquid, vapor pressure is also a function of temperature. Let us look at what happens when a liquid is heated in an open vessel. Initially, the liquid vaporizes only from the surface. On further increase in the temperature, vaporization occurs freely throughout the bulk of the liquid and vapor pressure rises. After some time, a stage is reached when the vapor pressure of the liquid becomes equal to the external pressure. This stage is called boiling, and the temperature at which boiling takes place is called the boiling point of that liquid. Hence, boiling point may be defined as the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. Do you know why food cooks faster in a pressure cooker? The boiling point of a liquid varies with the pressure. An increase in the pressure over the surface of the liquid increases the boiling point. In the pressure cooker, by covering the vent with a weight, the pressure inside the vessel is increased above the atmospheric pressure. Due to this, the boiling point of water also increases, and hence the food cooks faster. At high altitudes, the atmospheric pressure is low, and hence the water boils at low temperatures at these places. Hence, people living at higher altitudes use pressure cookers to cook food. The sterilization of the surgical instruments in autoclaves also utilizes the same principle as used in the pressure cookers. If the external pressure is 1 atmosphere, the boiling temperature is called the normal boiling point, and if the external pressure is 1 bar, the boiling temperature is called the standard boiling point of the liquid. The standard boiling point of a liquid is slightly lower than the normal boiling point, as 1 bar pressure is slightly less than 1 atmosphere pressure. For example, the standard boiling point of water is 99.6 degrees Celsius or 372.6 Kelvin, and normal boiling point of water is 100 degrees Celsius or 373 Kelvin. The variations in the vapor pressure of various liquids with temperature are as shown here. From the graph, you can see that the vapor pressure of a liquid increases with an increase in its temperature. That is, at normal room temperature, 298 Kelvin or 25 degrees Celsius, liquids like carbon tetrachloride, ethyl alcohol and water have a low vapor pressure. These liquids with low vapor pressure have a high boiling point and do not readily evaporate at room temperature. At room temperature, as diethyl ether has high vapor pressure, it has a very low boiling point. Therefore, it evaporates readily at room temperature. Let's now discuss about surface tension. This property of liquids arises from the intermolecular forces of attraction. A molecule in the interior of a liquid experiences equal intermolecular forces of attraction from all sides. Therefore, a single molecule in the bulk of liquid does not experience any net force. However, the molecules on the surface experience a net downward attractive force towards the interior of the liquid due to the molecules below it. Thus, we see that there is a tendency on the part of the surface molecules to go into the bulk of the liquid. The liquid surface is therefore under tension and tends to contract to the smallest possible area in order to have the minimum number of molecules at the surface. The attractive forces have to be overcome in bringing the molecules from the bulk to increase the surface of the liquid. This requires expenditure of energy. The energy required to increase the surface area of the liquid by 1 unit is defined as the surface energy. The units of surface energy are joule per meter square. Surface tension may be defined as the force acting at per unit length perpendicular to the line drawn on the surface of liquid. It is denoted by gamma and is measured in kilogram per second squared. Its SI unit is Newton per meter. To avoid the instability caused by the surface tension and to remain at the lowest energy state, liquids naturally tend to have the minimum number of high-energy molecules on the surface. To minimize the surface area as much as possible, the molecules of liquids assume the shape of a sphere. This is why mercury forms spherical beads instead of spreading on a surface. For the same reason, sharp glass edges are heated to smooth them. On heating, the glass melts and the surface of the liquid tends to assume rounded shape at the edges. This makes the edges smooth. This is called the fire polishing of glass. Due to surface tension, a liquid rises or falls in the capillary tube as soon as the capillary touches the surface of the liquid. Liquids wet the things because they spread across their surfaces as thin films. The particles of soil at the bottom of a river remain separated but are pulled together when taken out. This is because of the reduction in the surface area of the thin film of water. The magnitude of the surface tension of a liquid is directly proportional to the attractive forces between the molecules. This implies that the larger the attractive force, the higher the surface tension of a liquid. Surface tension decreases with an increase in temperature. This is because at higher temperature the kinetic energy of the molecules increases. This reduces the intermolecular attraction, resulting in a decrease in the surface tension. Let us now look at another important characteristic property of liquids: viscosity. We can observe that certain liquids flow faster than some other liquids. For example, water flows faster than honey. This is due to viscosity. Viscosity is a measure of resistance to flow in liquids, which arises due to the internal friction between the layers of the fluid as they slip past one another when the liquid flows. When a liquid flows over a fixed surface, the layer of molecules in immediate contact with the surface is stationary, while the upper layers move with different velocities. The velocity increases with the distance of the layers from the fixed layer. This implies that the uppermost layer of molecules has the greatest velocity. This type of flow, in which there is a clear gradation of velocity from one layer to another, is called laminar flow. As shown, for any layer in a laminar flow, the layer above it accelerates its flow, whereas the layer below it retards its flow. The velocity gradient is calculated as the difference in velocity between any two layers of the fluid, represented by du, divided by the distance between them, represented by dz. A force maintains the flow of layers, which is directly proportional to the area of contact of the layers and the velocity gradient. This implies that the force required for maintaining the flow of layers is a function of the velocity gradient and the area of the layers. In the equation shown, eta is the proportionality constant and is called the coefficient of viscosity. The coefficient of viscosity is defined as the tangential force per unit area required to maintain the unit difference of velocity between two layers unit distance apart. The SI unit for the viscosity coefficient is 1 Newton second per square meter, which is identical to 1 Pascal second. In the CGS system, the unit for the coefficient of viscosity is poise, named after the great scientist Jean-Louis Poiseuille. An increase in viscosity decreases the flow of a liquid. An example of a highly viscous liquid is the glass. Glass is so viscous that it would take years to move a few inches. The mobility of glass can be noticed by measuring the increased thickness of the window panes of old buildings at bottom of the window pane. An increase in temperature decreases the viscosity of liquids. At high temperatures, the molecules have high kinetic energy to overcome the intermolecular forces, thus allowing the liquid layers to pass over each other.